This next unit is all about chemical reactions. The previous units that you were studying, nomenclature, had to do with putting together chemical formulas. The next unit after that had to do with balancing equations, where you took those formulas and made equations. This next unit is all about taking those equations and understanding what's going on. There are 4 or 5 different types of reactions I want you to know. Combination or synthesis is when you take 2 or more elements and combine to make one product. Decomposition is where you have a single reactant that breaks apart into 2 or more different products. A single replacement reaction is where you take an element that replaces another element from another compound, and this happens in aqueous solutions. A double replacement, which also happens in aqueous solutions, is where there's an exchange of ions. Cations are exchanged and also anions. Usually occurs in aqueous solutions, and the products are either a precipitation, a gaseous product, or even water. Combustion reactions have to do with the reaction of oxygen. Okay? And when we combust a hydrocarbon, the products are usually carbon dioxide and water. Here are the different reaction types in kind of generic form. Notice in the double replacement, the A and the X swap. So we get AY and BX. In a single replacement, the A swaps with either the X or swaps with the Y. Okay? If that happens, the X will be alone or the Y will be alone. In decomposition, again, we have one reactant and it splits apart into many different products. In synthesis, we take many different reactants and we make one product. In combustion, that has to do with hydrocarbons. Okay, again, combustion has to do with the mixing of oxygen, produces carbon dioxide and water, always as a product. Another way to categorize reactions is the driving force or the cause. The driving force in reactions are one of 4 things: the production of a solid or a precipitate, production of liquid, usually the case is water, production of a gas, and a transfer of electrons. So let's talk more about a double replacement. In double replacement, again, just to recall, the 2 compounds exchange ions, and this happens in an aqueous solution. And when they exchange, 2 new compounds are formed. In double replacements, the driving force could either be a solid precipitate, a gas, or water. So here are 3 examples of different reactions. Highlighted in purple here are your driving forces. The first one is an example of a solid or a precipitate. That's the driving force of this reaction. The next one is the formation of a gas. And the last one is the formation of a liquid. And in this case, it's water. Okay? So it's really key when you take a look at these reactions to take a look at the states of matter to figure out what is the driving force. And again, all these have to do with aqueous solutions. Let's take a look at one example of a type of double replacement called acid-base neutralization. If we take a look here, we have an acid, which is hydrochloric acid. We have a base called sodium hydroxide, and we mix it. We always get water as a product. So the driving force for this reaction is always going to be liquid water when we take an acid and base and we mix them together. In chemistry, we need to write out the different equations to help us figure out what the driving force is for the reaction. Okay? The driving force is actually what is really going on the molecular scale. So, taking a look here, the three different equations are the molecular equation, which is a normal balanced equation, balance being the key. The total ionic is basically all the formulas broken up into ionic compounds, into individual ions, or BIPs. Okay, we've done this in the past. So all you do is you just do the BIPs for every single aqueous compound. And the net ionic equation is basically the total ionic equation where all the spectator ions have been removed. So taking a look here at the reaction that we just talked about, the HCl plus the NaOH, this is the regular molecular equation. Now another thing that you need to make sure you remember is that the equation needs to be balanced. And hopefully you'll notice on this equation that it is balanced. We have two H's, we have two H's. We have one Cl, we have one Cl, we have one Na, we have one Na, and we have one O and one O. So therefore we are balanced, and therefore we do not need to add coefficients. If the equation was not balanced, we then would have to add coefficients. The total ionic equation is where we take each one of these aqueous and we split them apart into individual ions. So HCl splits up into H plus and Cl minus. NaOH breaks up into Na plus, OH minus, and the same is true on the other side. The NaCl breaks up into Na plus Cl minus, but we leave, since this is a pure substance, we leave it alone as a together compound. The net ionic equation is where all the spectator ions, or the ions that have nothing to do with the driving force, are removed. So in this case, everything that has to do with the formation of water are H plus and OH minus. Okay, all the others are spectators. So we cross them out. The net ionic equation basically brings down the ions that have that contribute to the driving force, are brought down and in an ionic equation. So it looks like this. Okay, so notice how it is also balanced. We have two H's. We have two H's here. We have two there. We have one O and we have one O. Therefore, we're balanced. And that's it.